Greetings, my name is Dylan, and today I will give a summary of the paper MapReduce, Simplified Data Processing on Large Clusters. The paper introduces MapReduce, a programming model that allows developers to process extremely large databases across hundreds or thousands of computers. The main idea is programmers define only two functions, called map and reduce. The MapReduce system automatically handles parallel execution, data distribution, communication, load balancing, and machine failures. In the slides to follow, I will explain the motivation behind MapReduce, its programming model, how the system executes jobs, its fault tolerance mechanisms, its performance results, and its overall impact. Google needs to analyze crawled web pages, web page logs, search queries, and structure of links between websites. The actual computations were actually quite simple. For example, Google might count how many pages belong to each host or determine the most common search queries. However, the datasets were so large that these computations had to run across hundreds or thousands of machines. This created several difficult engineering problems. Programmers had to divide the data, assign work to machines, coordinate communication, balance the workload, and recover when machines failed. The purpose of MapReduce was to hide those distributed system details so developers could concentrate on the actual computations. MapReduce is based on two user-defined functions. The map function receives an input key and value and produces intermediate key-value pairs. The system then groups all intermediate values that share the same key. The reduce function receives one intermediate key and the complete collection of values associated with that key. It combines those values and produces the final output. The important point is that the programmer only writes the map and reduce logic. The MapReduce runtime handles the difficult work, including dividing the input, running tasks in parallel, moving intermediate data, handling machine failures, and writing the output. Because of this restricted programming model, the system can automatically determine how to distribute the computations. The paper uses word counting as a main introductory example. Suppose we want to count how many times every word appears in a large collection of documents. The map function reads a document. For every word it finds, it emits the word as a key and the number 1 as its value. For example, every occurrence of the word cloud produces the pair cloud, 1. The MapReduce system groups all pairs with the key cloud together. The reduce function then adds the values. If the word cloud was emitted 3 times, the reducer receives the key cloud and the values 1, 1, and 1. It produces the final result, cloud, 3. This simple example demonstrates how MapReduce converts independent records into grouped and aggregated results. Word count is only one possible application. The authors describe several other problems that can be expressed using MapReduce. Distributed grep searches large collections or files for matching lines. URL access frequency counting determines how often each web access address is requested. A reverse web link graph identifies all pages that link to a particular page. MapReduce can also generate term vectors, which summarize important words in documents, and inverted indexes, which are essential for search engines. For an inverted index, the map function emits a word and the identifier of the document containing it. The reduce function gathers all documents identifiers associated with that word. The system can even perform distributed sorting by emitting each record's sorting key and using the reducer's ordering behavior. This diagram shows the overall execution process. First, the input files are divided into M input splits. Each split typically contains between 16 and 64 megabytes in the original implementation. Next, the system starts multiple copies of the user program. One process becomes the master, while the remaining processes become the workers. The master assigns map tasks and reduce tasks to the available workers. A map worker reads its assigned input split, calls the user map function, and temporarily stores the intermediate key value pairs in memory. These pairs are then partitioned and written to the map workers on the local disk. The map tells reduce workers where those intermediate files are located. Each reduce worker remotely retrieves its assigned data, sorts it by key, and groups identical keys together. The reduce function is then called once for each unique key, and then the results are written to the final output files. When all tasks finished, the master informs the user program that the operation is complete. The master coordinates the entire operation. It tracks whether every map and reduce task is idle, in progress, or completed. It also records which worker is responsible for each active task. When a map task finishes, the master stores the locations and sizes of the intermediate files it produced. It then forwards the information to the reduce workers. The workers perform the actual computation. Map workers read input data and produce intermediate results. Reduce workers retrieve the results, sort them, group values by key, and execute the reduce function, and write the final output. This design centralizes scheduling decisions in the master while distributing most computation and data processing across the workers. Fault tolerance is one of MapReduce's most important features because machine failures are common in large clusters. The master periodically sends ping messages to each worker. If a worker does not respond, the master marks it as failed. Any task that was running on that worker is reset and assigned to another worker. Even completed map tasks may have to be repeated because of their intermediate output is stored on a failed worker's local disk. Completing reduced tasks normally do not need to be repeated because their results are stored in the global file system. To prevent incomplete or duplicate output, tasks are initially write to temporary files. A completed reduced task automatically renames its temporary file to the final file name. When a map and reduce functions are deterministic, the authors state that the distributed execution produces the same results as the corrected sequential execution. The master itself was a single point of failure in this version. If it failed, the entire operation was aborted and could be restarted by the client. The system includes several important optimizations. The first is data locality. Instead of transferring large input files across the network, the master attempts to run a map task on the machine that already stores a copy of the required input block. This reduces traffic network. Second, MapReduce creates many more tasks than there are worker machines. Fine-grained tasks improve load balancing because fast workers can process more tasks, while the work from failed machines can be distributed across the remaining cluster. Third, the system handles stragglers using backup tasks. Near the end of a job, it launches duplicate copies of tasks that are still running. The first copy to finish is accepted. Finally, a combiner function can partially aggregate repeated intermediate values on the map worker before the data travels over the network. In word count, for example, thousands of local word1 pairs can be combined into a single partial count. The authors evaluated MapReduce on a cluster of approximately 1,800 machines. Each machine had two 2 GHz Intel Xeon processors, 4 GB of memory, local IDE disks, and a gigabit Ethernet connection. The first experiment performed a distributed grep operation over approximately 1 terabyte of data. It reached a peak input processing rate of more than 30 gigabytes per second and finished in about 150 seconds. About 1 minute of that time was startup overhead. The second experiment sorted approximately 1 terabyte of data. The job used 15,000 map tasks and 4,000 reduced tasks. The complete sorting operation finished in about 891 seconds, or just under 15 minutes. The authors noted that this performance was comparable to the best reported TerraSort result at the time. One of the strongest parts of the paper is the comparison shown in Figure 3. During normal execution, the sorting operation completed in about 891 seconds. When backup tasks were disabled, several slow reduced tasks were create a long tail in the end of the job. The total execution time increased to 1,283 seconds, which was 44% longer. In another experiment, the researchers intentionally killed 200 of the 1,746 worker processes while the sorting job was running. The master detected the failures and reassigned the lost work. Even after such a large number of worker failures, the job completed in 933 seconds. That represents only about 5% increase compared with normal execution. These results demonstrate that redundant execution and automatic task re-execution can provide strong resilience with relatively low performance overhead. MapReduce was rapidly adopted within Google. The number of MapReduce programs in Google's sort tree grew from 0 in the early 2003 to almost 900 by September of 2004. For a subset of jobs run during August 2004, the system processed 29,423 jobs and read more than 3,000 terabytes of input data. One of the most significant applications was a rewrite of Google's production web indexing system. In one indexing phase, approximately 3,800 lines of C++ code was reduced to about 700 lines using MapReduce. The new indexing system was easier to understand, modify, and operate because fault tolerance, scheduling, and parallelization was handled by the framework. The paper's main lesson is that restricting programmers to a simple MapReduce model enables the system to automate large-scale parallel execution. Data locality reduces network traffic, fine-grained scheduling balances the workload, and redundant execution handles failures and slow machines. Overall, MapReduce made large-scale distributed data processing accessible to programmers who did not necessarily have the expertise in distributed systems. Its ideas later influenced systems such as Hadoop and many modern data processing platforms. And here's my reference. All the information and diagrams used in this paper are used from the paper MapReduce, Simplified Data Processing on Large Clusters. And thank you for listening.